Welcome back to Mathematical Statistics. I'm really sorry about having to cancel my office hour today. I, in fact, had to cancel every single meeting I had today and barely made it here due to reasons. I'm going to make some office hours for this weekend, but also wanted to pay special attention to the homework in this part where I say, how's the homework going? Let me bring up the homework for myself. Okay, so problem one is just plug and chug. We developed two formulas, x bar plus or minus something times sigma over the square root of n. And you just have to decide whether a z, or standard normal critical value, or a t is appropriate. And get that number out of any table or any software. And it's a numerical, quick result. So I don't think there's anything to say about that unless you want to ask specifically something about problem one. Okay. 2 is long, at least long looking, and I'm going to come back around to 2 because my first example today is going to be very similar to 2. So I want to talk about 2 after we do this example. So I'm going to skip ahead to 3. Okay, so 3 is a confidence interval for the parameter lambda for an exponential distribution. Oh no, I gotta stop my recording. And we did one in class. And we used the minimum as the statistic on which we're going to base our confidence interval. And because the lambda is kind of 1 over the mean, it's much more natural to think about making a confidence interval based on the statistic x bar. But the reason I use the minimum is because we know the distribution of the minimum. Well, we know both, but the distribution of the minimum is exponential, which is nice and easy to work with and integrable, and we can get exact critical values. So on the homework for problem 3, this is 3, right? Yeah. You are supposed to come up with a confidence interval for lambda based on the sample mean. And it says to leave the results in terms of a chi-squared critical value. So that means there's going to be some chi-squared curve with some specific kind of degrees of freedom. That's horrible, but and so I don't know what it's going to be in the problem yet. Well, I do, but this is a chi-squared n PDF. And so you're going to want to find two numbers that capture the right area. And so, for example, if you put them quote unquote in the middle, and what the heck is the middle here? I guess the middle would be to put alpha over 2 on each side. You don't have to do this. You could start from 0, or you can go from something up to infinity. But I just want to remind you that we have notation here. So if we had put area 1 minus alpha in the middle, there's alpha over 2 up here and alpha over 2 down here. And so you can actually write on your homework A and B if you draw the picture, or if you say where A is the number that cuts off alpha over 2 area to the left, and B is the number that cuts off area alpha over 2 under the chi-squared PDF to the right. But if you want to get on board with the critical value notation, this right value is usually called chi-squared sub alpha over 2. And then we need something that tells us what degrees of freedom this depends on. So either a comma n or a chi-squared alpha over 2 of n. And it's not completely universal that the alpha over 2 subscript is the area to the right. So be careful if you're reading websites or other books. The critical value, like a z sub alpha, could possibly, but not likely, cut off alpha area to the left. And then if we have, for our lower critical value, alpha over 2 to the left, then we have 1 minus alpha over 2 to the right. So I would call this chi-squared 1 minus alpha over 2, and then an n. I don't think you can really read that alpha, but I think you know what I mean, hopefully. Okay, so how do we make this apply to our confidence interval? So we want to make a confidence interval based on x bar. Now, x bar being a constant times the sum of the x's actually has a gamma distribution, but you may be more comfortable at this point with the gamma distribution given by the sum of the x's. if you want to make an interval based on the sum of the x's, in the end, you'll have like a function with the sum of the x's somewhere and, on both sides. You could go ahead and do that, and then you can turn it into a confidence interval based on the mean, because you can run through your confidence interval and put in an n 1 over n everywhere and rewrite it as n times x bar. So that's only if you're more comfortable working with the sum of exponentials than the sample mean. But yeah, let's write down a distribution for the sample mean. We know that the sum as I goes from 1 to n of the xi has a gamma distribution with parameters n and lambda. We showed that using moment generating functions, and that's really common knowledge at this point for us. And we showed that if x has a gamma distribution with parameters alpha and beta, and if c is a constant greater than 0, then c times x has a gamma distribution with parameters alpha and beta over c. And so we can take that little aside there to get the distribution of x bar. So in this problem where we have exponentials, x bar is 1 over n times this sum, from 1 to n. Oh, I got a new, where is it? I got a new dental appliance from my neighbor. It's still sealed because it's kind of gross. It's got fleshy bits on it. It was a crown removed with the root and everything. I don't know if you can see that. There's blood on it, and I don't really want to unseal it yet, because although I like to collect old weird teeth things, I don't really want to touch my neighbor's gums. But back to the problem. I'm going to write x bar as 1 over n times this sum, and so we know that that sum has a gamma distribution. So this is a constant like the c, and that c goes under the second parameter of the gamma distribution, and the particular gamma distribution is up here. And so we end up with a gamma n n lambda. Does that make sense? Okay, cool. Stop me if you need to. Okay, so this is the statistic on which we're going to base the confidence interval. And I sometimes say estimator because that's kind of what I think about when I do these. Like, you want to estimate a mean, so you're going to estimate it with the sample mean. But really, you can use any statistic. It doesn't have to be an estimator or a good estimator or something that makes sense. It just has to be something you can work with. And so step 1 for every confidence interval is to pick a statistic, and in this case it was picked for you. And then step 2 is to find a function of that statistic and the unknown parameter, in this case lambda, whose distribution is known to you and is parameter free, or at least unknown parameter free. So if there's multiple parameters and there's one it's okay if that's in there. So I don't like the fact that the lambda, the unknown parameter, is in this distribution. It's not unknown parameter free. So what if I multiplied by lambda, my x bar, then that lambda is going to end up under that second parameter in the gamma distribution. So I'm going to get a gamma n, right? And that comes from n lambda over lambda, just using, again, the thing in the circled blob. Now I have a distribution that doesn't depend on any unknown parameters. But how do we get a chi-squared? So remember that a chi-squared with n degrees of freedom is defined to be a gamma n over 2, 1/2. And whenever we have a gamma with an n 1/2, we can write that as a gamma 2n over 2, 1/2. And then we can see it as a chi-squared. So I can take care of the n over here, but I do need a 1/2 in the second position. So why don't I and you would probably do this all in one step, but I'm just kind of breaking it down. If I multiply by n, then that will cancel out that n, and I'll have a gamma n1. And I'll leave it to you to multiply this guy by a constant that will get you a 1/2 in the second argument for the gamma distribution. And then once you have gamma n 1/2, you've got a chi-squared random variable. And so whatever you're left with on the left side, when you get that chi-squared, is going to be your pivotal quantity. So this thing circled but adjusted a little more so that the second argument is 1/2 is the thing that you put between two chi-squared critical values. And I was going to do my air quotes, but I've twisted my eye pen in my hair in a rubber band on my, I'm kind of stuck. Technical difficulties. Okay, so solve for lambda in the middle. After, again, doing one more transformation here in order to get this to look like a gamma n 1/2, which is a chi-squared 2n. Questions?
I had a question.
Yeah.
So in your like list of steps for finding
the confidence interval?
Yeah,
Mm-hmm.
Which, and this may just be a product of that list kind of changing over the course of yesterday's lecture, but I had the first step is find an estimator theta hat for theta.
Yeah.
And so is that a little bit just kind of wrong wording, and really we just want to find a statistic that involves theta?
Yes, and I can also defend the wording, but you're right, it's just not the best wording. So any statistic could be an estimator. So it doesn't really have to, you know, make sense. But it looks like the way I wrote it that we're looking for something that makes sense.
Because in this case, X bar is an estimator, or like a good estimator, I guess, for 1 over theta.
Yeah.
Okay, but we just want something that involves theta.
Yeah.
Or lambda in this case.
Yeah, so although that wasn't wrong, I would like to change number 1 to find a statistic on which you can base your confidence interval. And the goal is something some statistic that you can manipulate to come up with a function of that and the parameter whose distribution you know. Yeah.
Okay, thank you.
We're going to learn how to estimate soon, but we're still at the part of the course where I'm going to say find a confidence interval based on this statistic, unless it's maybe a couple of cases where you're looking at the mean, and I think you're going to automatically go to the sample mean, hopefully. Okay, let me look at the next problem here. Ooh, I love this one. The next problem, we're revisiting something from homework 3, problem 7, which if you downloaded this current homework immediately, that was wrong there. I had to fix that reference. So if you downloaded and printed it, you might not have the right reference to the old problem. But in problem 4, here's where it gets, I think, really cool. We showed in homework 3, problem 7, that if you have X with let me be more specific, a random sample X1 through Xn, IID from a distribution with common CDF F, then you showed on this previous homework that -2 times the sum as I goes from 1 to n of the log of f of xi has a chi-squared distribution with 2n degrees of freedom. Yeah. And the purpose of this problem is to show you how to make a confidence interval for the gamma parameter of the Pareto distribution. And so if you're thinking about the Pareto distribution with parameter little gamma, first you have to come up with a statistic, maybe an estimator of gamma, maybe not, although any statistic is an estimator. And then you're going to have to find something you can work with that you can make a pivotal quantity. And so that's a hard thing in general, but this problem is leading you through a very specific example. So in part A, you weren't supposed to really do any extra work, but you were supposed to show that -2, or at least state or argue that -2 times the sum of the log of 1 minus f of xi has the same distribution. And I guess this depends on how you showed the first result back in homework 3. So the way I showed it was to start in steps. And maybe you didn't do this, but the first thing I looked at was yi defined to be the CDF evaluated at the random quantity xi, and I showed that was uniform 0, 1. I'm almost finishing this. The guilt is strong about my office hour today. The argument that you can replace let me get a color, this f of xi here with a 1 minus f of xi is just the argument that this is a value that is uniformly distributed between 0 and 1. And when you take 1 minus that, it's still equally likely to be anywhere. So if your value that's uniformly distributed between 0 and 1 came out to be 1/4, 1 minus that would be 3/4, but you'll just as likely get 3/4 with 1 minus that will give you 1/4. So that's all I was looking for part A, is just not really doing the work, but kind of convincing yourself that that has the same distribution. And so if it does, and it does, then we can say, because of this, we can say that -2 times the sum as I goes from 1 to n of the log 1 minus capital F xi is also chi-squared to n, because it starts with that same, depending on how you proved it, but given the way I proved it, it starts with that same building block of a uniform in the center there. Okay, so the goal is to find a confidence interval for the gamma in the Pareto distribution, and it's all right here in front of you. So just write the CDF for the Pareto and plug it in. And the reason I changed it from the log of the CDF to 1 minus to log of 1 minus the CDF was to get rid of the 1 minus in the Pareto CDF and make something that is easily solvable for the gamma in the middle. You're going to want to put this quantity in between two chi-squared critical values, and then you want to solve for gamma in the middle. And if I use the original formulation of this statistic, I can't solve for gamma in the middle. But if I use the 1 minus version of it, it's pretty easy. Okay. Okay, and finally on problem 5, we're gonna need this result today. And so I was just gonna say, oh, things get large, things get close, but I wanted to make sure you saw it. My recommendation for problem 5, it's a convergence improbability problem. It looks really messy, but my recommendation is to look to remove the square roots, and then you can put that convergence improbability through the square root. So I would show that S1 squared over N1 plus S2 squared, these are two sample variances from two different populations, over sigma 1 squared over N1 plus sigma 2 squared over N2. I would show that this goes in probability to 1, and then you can put it through the function g of x equals the square root of x. And personally, you guys haven't embraced it yet, but personally, I would use that theorem on this. So I would show that the expected value of this left-hand side is 1, and that the variance of this left-hand side is going to 0. And that's enough to get this conclusion. And it looks like a real nightmare mess, but if you were computing, say, the variance of the left-hand side, so you'd have this, all of this stuff. The denominator, the sigma 1 squared plus the sigma 2 squared, each over their own ends, is a constant. It's not random. And you could pull that out and it will come out squared, as things do out of variances. And in there is the S1 squared over N1 plus S2 squared over N2. And they're given in problem 5 to be independent random samples. So that means that when you're computing the variance of S1 squared over N1 plus S2 squared over N2, these two guys are independent. And so by independence, you can break this up into a variance plus a variance. I'm purposely being a little sloppy and fast because I wanted to leave you something to do if it's only just to put back the pieces of everything I'm writing down. But if you'd like me to go back over something, let me know. The last thing I want to say about this problem, if there are no questions, is how to find those individual variances. The variance for a sample variance is in general a very hard thing. It's a very ugly thing. It involves that fourth central moment, but this is the normal distribution. And so you should use the fact that we know that if x1 through xn are IID, normal, mu, sigma squared, we showed that n minus 1 s squared over sigma squared is chi squared n minus 1. So this is another one of those aside blobby things, not the notation of this problem. So check this out. If I want to find the variance of s1 squared over n1, I'm going to pull that n1 out, so I'll get 1 over n1 squared, variance s1 squared. And then how do I do that? I don't know the distribution of S1 squared. I do know the distribution of S1 squared times N1 minus 1 over sigma 1 squared. So write it that way. This is 1 over N1 squared, the variance of N1 minus 1 S1 squared over sigma 1 squared times sigma 1 squared over N1 minus 1. And in doing that, you have just created another constant which gets pulled out of the variance and comes out squared. And then you're left with a variance of a chi-squared n1 minus 1 random variable. We saw that the variance of any chi-squared with n degrees of freedom is 2n, but if you don't remember that, then translate back to the gamma and look it up. That's pretty clever, if I say so myself. I just love that sort of thing. You know, make it look like something you know and pull all the constants out that you had to, what is the word, compensate with. Okay, any questions? Okay. So I said I would go back and talk about 2, but it's really close to an example we're doing today. So I wanted to do that first. So I'm out of the homework, and this is some new stuff. Well, it's one more confidence interval. So I'm just in a running sort of list of examples of confidence intervals. And here is the next example, actually the last one we're going to do for now. And then after we learn how to estimate things, we're going to come back and use our estimators to help us find more complicated confidence intervals. But in this case, I'm going to assume that I have, let's say, suppose I have 2 independent random samples. Independent random samples. So one of them is going to be of some size n1 from a normal distribution with its own mean and its own variance. So one of size n1 from a normal mu1 sigma 1 squared, and then the other from a different normal with a different sample size. One of size n2. So far, this is kind of looking like problem 2, but this is the easier version. I'm going to assume that sigma 1 squared and sigma 2 are known, and if they are, I'm going to try to come up with a confidence interval for the difference between the means. That should be a mu2 in my second normal distribution. I wrote mu1 again. So I'm going to assume that sigma 1 squared and sigma 2 squared are known. Again, it's like our step 1 building block for making more complicated scenarios here. And I want a 100 times 1 minus alpha % confidence interval for the difference between the means, the true means, mu1 minus mu2. And we're going to hit hypothesis testing today, at least our brief intro, and then we're going to really get serious about estimation and do all our formal forms of estimation. But a confidence interval can sort of stand in as a hypothesis test. Something you might want to test is grab the samples and figure out maybe if the means are the same. The confidence interval for mu1 minus mu2 is going to be an interval of plausible values. And if that includes 0, then you're saying that it's reasonable that mu1 minus mu2 can be 0. So you're saying it's reasonable that mu1 can equal mu2. So in this sense, a confidence interval can kind of serve as a hypothesis test if you set things up right. But we already know how to do this. I meant to look at my steps and really solidify this. So the first one is to come up with a statistic that we can use. Estimator or statistic. And because I want to estimate a difference between two means, I think the very natural thing to do would be to take the two sample means. So how about we look at the first sample mean minus the second sample mean. I didn't really want to bring all the notation into this problem, but the first sample, I'm just going to write in the middle. I'm going to mess this up and then I'm going to erase it. The first sample you can maybe think of as x11, x12, out through x1, n1, and the second x21, x22, x2, n2. And then this is going to be the mean of the first sample. So it's going to be a 1 over n1 times blah, blah, blah. And this one's going to be the mean of the second sample. But I just didn't want to explicitly write out the data like this. But again, if I did, then xi bar would be 1 over ni, the sum as j goes from 1 to n of xij. And that is overkill for this problem. Why should we have to think like that on a Friday? Okay, so I picked the kind of natural statistic that you would use to maybe make inferences about the quantity mu1 minus mu2. And then the next thing, I don't know which step this is. Maybe this is still in step 1. We're looking at the distribution of this, because then in step 2, I want to come up with a pivotal quantity. So a function of this and the thing I'm trying to estimate, whose distribution is unknown parameter free. So I don't know where I put this distribution. I'm really sorry, I meant to check this out. What is the distribution of x1 bar minus x2 bar? we know that x1 bar is normally distributed. Let me do this kind of on the side. It's normally distributed with the mean from the first distribution, mu1, and the variance, sigma 1 squared, divided by the number of things, n1, that made up that x bar. Let me try to get this out of the corner here. And similarly, we know that x2 bar is normal. Not using the central limit theorem, I'm using the fact that a linear combination of normals is normal. And so this is, oops, sorry. This is going to be normal with a mean mu2 and variance sigma 2 squared over n2. And the two samples were independent. So to get the distribution of this quantity, x1 bar minus x2 bar, it turns out that any linear combination of normals is normal also includes dependent normals, although we haven't talked about dependent normals yet. So you don't even need independence to be able to conclude that this is normal, just for the record. But in our case, they are independent, and because they're independent, so again, this is normal because it's a linear combination of normals, and we know the mean, right? We know the expected value of x1 bar minus x2 bar. That's the expected value of the first guy minus the expected value of the second guy, and that's mu1 minus mu2, which is unsurprising. And the variance of x1 bar minus x2 bar, because they're independent, we get to break this up into two pieces. I mean, we get to kind of distribute the variance. And the negative goes away because you can think of it as x1 bar plus -1 times x2 bar and distribute the variance across and then pull out that -1, but it will come out squared. So we're going to get the variance of x1 bar plus the variance of x2 bar. And we know these. This is sigma 1 squared over n1 plus sigma 2 squared over n2. And in this simple example, those sigmas are known to us. All right, so stop me if there's any questions, but on to possibly step 2. Dang it. I think this might have been step 3. I should just not label them with numbers, but there are some distinct steps here. So I'm going to come up with the pivotal quantity, a phrase that I never used before and just gave you for the record, but now I've used it at least 10 times, so I guess I'm hooked. Pivotal quantity, oops. So this is a function of the statistic we're going to use, which is x1 bar minus x2 bar, and the thing we're trying to estimate, which is mu1 minus mu2. By the way, I forgot to finish off my statement about normality that is now in the center of the screen. I'm going to put in my variance, sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so we know how to do this. We've got a normal, and its mean is the thing we want, and why don't we just standardize it? So I'm going to take x1 bar minus x2 bar, and I'm going to subtract the mean, mu1 minus mu2, and I'm going to divide by the standard deviation, which is the square root of the variance. So it's actually a big square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And this is a nice normal that has been centered at 0 and now has variance 1. So we can call it z, and we can put it between two z critical values from the standard normal table, and then solve for mu1 minus mu2 in the middle like we always do. So if I call it Z, which is our preferred letter for a normal 0, 1, then I know that I get probability 1 minus alpha if I put Z between Z alpha over 2 and the negative of Z alpha over 2. And then I'm just going to plug in what we have, which I will spare you. I'm just going to, that is a lowercase thing. I need to make that appear a little smaller. Negative Z alpha over 2 less than the giant circle, less than Z alpha over 2. I'm on a tablet, and this is literally what cut and paste is for, but the thing in the circle is still the thing in the circle. And then we want to step 3 or step 4, solve down to get mu1 minus mu2 in the middle. So like, I give up on the numbers. Step 3, solve for the thing we're trying to estimate, mu1 minus mu2 in the middle. And when you do, you'll get the two endpoints. You'll get x1 bar minus x2 bar minus z sub alpha over 2 times this ugly, huge square root. Let me make some space here. Oh, I grabbed a mu. I think I'm going to put my new tooth out in my backyard and let insects clean the flesh off. So why not? Okay, so continuing, finishing. You know what? I think that's an N1, not an N2. And rather than write the two endpoints of the interval, I am going to shortcut this and replace the minus in front of the critical value with a plus or minus. We are done. Questions? Wow, okay. Okay. We can generalize this example. If we don't know sigma 1 squared and sigma 2 squared, which we likely don't, if we replace them with the sample variances S1 squared and S2 squared, if the sample size is large, then our statistic, our pivotal quantity, is still approximately normal 0, 1. And that is the purpose of the last homework problem. Because, okay, so here's what I want to say. So suppose that sigma 1 squared and sigma 2 squared are unknown, but the sample sizes N1 and N2 are large. Both of them. Then S1 squared, the sample variance for the first sample. So if you did actually write my double subscript notation, then S1 squared is going to be the sum as I goes from 1 to N1 of x 1i minus x1 bar squared over N1 minus 1. You know what it is. You don't want to get bogged down in this notation. It's the sample variance for the first sample. And S2 squared is what it is. So if the sample sizes are large, then S1 squared, I'm claiming, and S2 squared are getting close to sigma 1 squared and sigma 2 squared. So to finish this sentence, I'm going to say these are good approximations to sigma 1 squared and sigma 2 squared. And the purpose of homework 6, problem 5, is to make this statement a little more formal. Because if you're using S1 squared and S2 squared, then you're going to take your difference in sample means and standardize them by subtracting the mean and dividing by kind of a sample version of the standard deviation. And I'm claiming that this is approximately, I'm not using asymptotically, it is an asymptotic result, but I don't really want us to think that hard. It's roughly, as n gets large, normal 0, 1. And to formalize that statement, you would use Slutsky's theorem. And you would say that you know this distribution if you had the sigmas. So this is since. All right, I already had a circle and I don't want to write this again, so let me make a weird squiggly box. Since the weird squiggly box is equal to x1 bar minus x2 bar minus mu1 minus mu2 over, I'm going to put the sigmas back in, sigma 1 squared over n1 plus sigma 2 squared over n2 times, or divided by, but I'm going to say times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 all over and still under the square root s1 squared over n1 plus s2 squared over n2. This first guy is either normal 0, 1 if we started with normals, or asymptotically normal 0, 1 if we didn't start with normals, but we had large samples and we used the central limit theorem. So this is either normal 0, 1 or approximately normal 0, 1 by the central limit theorem. And so we can say that this is like a z, and its distribution does not depend on n. Assume that I started with normal samples here, so we're not trying to use the central limit theorem. So the first circle here is a sequence of random variables that are all normal 0, 1. They're converging in distribution to a normal 0, 1. By Slutsky's theorem, if we can say that this other circle is going to 1, then we can say, so this is either going in distribution to a normal 0, 1. Well, it is. So it's either going in a boring way, where we started with normal, so it was already normal 0, 1, or it's going in a slightly more interesting way, where we're using the central limit theorem. And I claim that this is going in probability to 1. And so it's a Slutsky's theorem result to say that this thing in the squiggly box back up here is converging in distribution to a normal 0, 1 times 1, or a normal 0, 1 by Slutsky's theorem. I know that was really rushed, but I just wanted this to be kind of broad strokes because we'll never get to do anything else than this one example if I really did it in slow motion. So I'm saying you can use S1 squared and S2 squared if you have large samples. And the reason is because of this convergence in distribution result, which comes from Slutsky's theorem. And you can use that once you've shown that this guy is going to 1, and that is homework problem number 5. Questions? Anyone have a joke?
No, but I can't stop thinking about how you obtained this tooth. Like, what is the conversation that had to be had?
Oh, yeah, I ran into my neighbor in the driveway and he was going to get a tooth pulled and I was like, please, please bring it back. And he's heard it before. I have another one of his teeth. I don't even know his name, but he's my neighbor and I have 2 of his teeth. Okay, that was better than a joke. That was a story. Okay, so the last thing I think we can do today is What if you have x1 through xn? No, I've got two samples. I really do want to use cut and paste this time, so forgive the scroll. I'm going to use the same kind of setup as the last example. Oops, what? All right. Okay, so sorry, I know you're not seeing this part. It's just a cut and paste and you're not seeing my little lasso. So it just looks like I'm wildly scrolling around for no reason. But it didn't cut the first time. This is why I don't bother to do this. All right, let me get a new slide. I want to go back to this example. And I also want to assume that the sigma 1 squared and sigma 2 squared are unknown. And actually, while I'm at it, the mu's. And I want a 100 times 1 minus alpha % confidence interval for mu1 minus mu2. And I'm rushing, so I didn't write that that's unknown, but you wouldn't be finding a confidence interval if you knew it. Right, so if we know the sigma squareds, we can use a nice standard normal for our pivotal quantity. If we don't, but we have large samples, we can use something that is approximately standard normal for our pivotal quantity. But I in this case, have at least one small sample. Okay, so either N1 or N2 is less than 30. Okay, I think a T is in order here. If the underlying distribution is unknown to us and we have small samples, there's nothing to do. But with normality, we might be able to build a T out of this. And this problem is kind of easy if you can assume that sigma 1 squared is equal to sigma 2 squared. We can actually do a hypothesis test once we learn what that is to test whether or not we think that's reasonable. And in that case, problem 3 on the homework is leading you through the construction of building this confidence interval. Now, if you can't assume sigma 1 squared is equal to sigma 2 squared, then there is no exact answer to this. This is a hard problem known as the Behrens-Fisher problem. And I'm out of time, but there's something known as Welch's approximation. You do not need to know this. You do not even need to write this down. I will never bring it up. But some guy named Welch, he figured out an approximate t distribution in the case when sigma 1 squared is not equal to sigma 2 squared. So in the case that they are assumed to be equal, that is homework problem number 3. And it is a walkthrough, and it is devising a t pivotal quantity. Any questions with that? So I guess I had time to write the punchline here, right in here, which is if we can assume that sigma 1 squared is equal to sigma 2 squared, we can look at the blah, 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 blah. We can look at this. No, sorry. We can look at this and we can get a t distribution. Small samples starting with normals. And again, that's homework problem 3. So I am out of time. And yeah, I guess we're done. Have an awesome weekend. I will have some extra office hours this weekend. As soon as I get through colloquium, I will figure out what they are. And if you can't make them, let me know. And, you know, I will make sure I can meet you because of the office hour guilt. Thank you.
Thanks, Jem.
Yeah.